Welcome to the video on the capacitance and voltage characteristics of the mass capacitor. So in the previous videos, we have discussed about what is meant by mass capacitor, how to understand the working principle of mass capacitor using the energy band diagram. So we have three regions of operation. That is, one is accumulation, then the space charge formation, space charge region formation, and the third one is inversion layer formation. Now, in this video, we will be discussing about what is the capacitant voltage characteristics in these three regions, and also we will be studying about the frequency effects. So coming to the capacitance, we know the capacitance of the device is defined as C is equal to dq by dV, where dq is the magnitude of the differential change in the charge on one plate as a function of the differential change in the voltage dV across the capacitor. So capacitance is nothing but the rate of change of the charge with respect to the rate of change of the voltage. The capacitance is a small signal or an AC parameter, and it is measured by superimposing a small AC voltage on an applied DC gate voltage. The capacitance then is measured as a function of the applied DC gate voltage. Coming to the characteristics of a mass capacitor, we have the mass capacitor as metal oxide and semiconductor. Consider a p-type semiconductor material, and then the energy band diagram of this will be like in a p-type semiconductor. This during the accumulation, the energy band will be slightly curved up at the junction or at the interface of the oxide and the semiconductor material. So mass capacitor with a p-type for the case when a negative voltage is applied, that is when a negative voltage is applied to a p-type semiconductor, it results in the accumulation layer of holes in the semiconductor at the oxide semiconductor interface. So now a small differential change in voltage across the mass capacitor will cause a differential change in charge on the metal gate and also in the whole accumulation charge. The differential change in charge density occurs at the edges of the oxide as in the parallel plate capacitor. So the change in the capacitance will be equivalent to the change in the voltage which is applied. So that is dq dash is nothing but the change in the charge carriers and due to the applied gate voltage. So the capacitance per unit area of the mass capacitor for this accumulation mode is just the oxide capacitance, or I can say that C accumulation is nothing but COX is equal to EOX by TOX, where EOX is the permittivity of the oxide layer and TOX is nothing but T suffix OX is nothing but the thickness of the oxide layer. So here in accumulation, this mass capacitor acts like a parallel plate capacitor. So coming to the next one, that is when a slightly positive voltage is applied to the gate, including a space charge region in the capacitor. So a space charge region will be formed, and the energy band diagram is such that and the band structure will be bending downwards slightly. Here now the oxide capacitance and the capacitance of the depletion region both will be occurring in series. A small differential change in the voltage across the capacitor will cause a differential change in the space charge width. So here the depletion capacitance will be in series with COX and CSG, and hence we can say that C depletion is equal to COX into CSD divided by COX plus CSG. That is, we can say that C depletion is equal to epsilon OX by TOX plus epsilon OX by EX into XT. So the minimum capacitance will be occurring when there is a change from the depletion region, formation of the depletion region to the formation of the inversion region. So now coming when the voltage applied is increased, that is when more positive voltage is applied, a small incremental change in the voltage across the mass capacitor will cause a differential change in the inversion layer charge density. So this energy band diagram is for a mass capacitor for the inversion mode. And in the second diagram, we can say the differential charge distribution at the inversion at for a low frequency differential change in the gate voltage. The space charge width does not change. If the inversion charge can respond to the change in capacitor voltage, then the capacitance is just the oxide capacitance. Again, C inversion is nothing but epsilon Ox divided by Tox. So we have got three different capacitance, the three dashed. So when we put together all the three different types of capacitance, we can see that in this graph, that is the first is the accumulation, followed by the depletion, and then the inversion. So the moderate inversion is the transient region between the point when only the space charge density charges with gate voltage, and only the inversion charge density with gate voltage. The point on the curve that corresponds to the flat band condition is of interest. The flat band condition occurs between the accumulation and the depletion condition, that is the CFB. The CFB is the flat band condition, and it is given by CFB dash is equal to epsilon of oxide divided by TOX plus epsilon of DOX by EX into root of KT by E into EX by NA. The flat band capacitance is a function of oxide thickness as well as the semiconductor doping. So here we can see that the frequency due to the change in the voltage, the capacitance will be first it will be flat for the accumulation region, and then it decreases, the capacity effective capacitance decreases due to the formation of the depletion region, and at the moderate inversion we can see that again it increases, and at strong inversion my COX is only the capacitance available at the strong inversion period, and hence it remains constant. This is for the p-type semiconductor. So similarly, when we have the n-type semiconductor, the graph given here gives the ideal capacitor for with the n-type substrate by changing the sign of the voltage axis. So the accumulation condition is obtained for the positive gate bias, and the inversion condition is obtained for the negative gate bias. So here we can see that the accumulation is constant. At accumulation region, it is constant, followed by a decrease in the capacitance in the depletion region, and then the capacitance increases for the moderate inversion, and again the strong inversion, the capacitance is constant. So here the capacitance at accumulation and strong inversion is only due to the oxide capacitance, whereas in the depletion region, the capacitance is due to the uh, oxide capacitance as well as the depletion capacitance. Okay, coming to the frequency effects, there are two sources of electrons that can change the charge density of the inversion layer. That is, the inversion layer which is formed is due to two charges, that is, one is diffusion of minority carrier electrons from the p-type substrate across the space charge region, and also by the thermal generation of electron hole pair within the space charge region. So both these processes generate electrons at a particular rate. The electron concentration in the inversion layer cannot change instantaneously. If the voltage across the mass capacitor changes rapidly, the change in the inversion layer will not be able to respond. That is, we can say that at high frequency, the change in the voltage will not have the similar effect in the change in the capacitance as the low frequency. Then the CV characteristics will be function of the frequency of the AC signal used to measure the capacitance. So the bottom graph gives the variation of the capacitance along with the voltage for the high frequency as well as the low frequency. High frequency, it corresponds to the value of the order of 1 megahertz, and low frequency corresponds to the value in the range of 5 to 100 hertz. So in the high frequency, we can say that the inversion will not happen immediately. That is, here we can see that for the low frequency is nothing but the frequency of about 5 to 100 hertz, where the change in the voltage will result in the equivalent change in the capacitance. But the high frequency capacitance will not have an immediate effect, and we can see that the capacitive capacitance will be changing as it will be remaining constant even if the voltage is increased. So here in this video we have discussed about what is meant by capacitance and voltage characteristics. that is the variation of the capacitance with respect to the applied voltage in the mass capacitor and also with respect to the frequencies. Thank you.